In our last video, we introduced improper integrals where the integrand was discontinuous at a point. In particular, we had an infinite discontinuity. Here we're going to discuss a different type of improper integral. So here we're going to talk about improper integrals over an infinitely long interval. Over an infinitely long interval. So again, we're going to divide it up into several cases. Case 1. For case 1, we're going to suppose that our function is continuous, but for an interval extending off to positive infinity. So if f is continuous on an interval that looks like a to infinity, where a is some finite number, then the improper integral from a to infinity of f of x dx is equal to, well, what's this going to look like? We're imagining that we have some interval which is infinitely long, something like this. So this is our x-axis here. Let me just move this down. So let's decide what should be the definition. We're going to have some function which extends off indefinitely. Let's say that this is a, and we want to compute the indefinite integral, or rather the improper integral from a off to infinity. So we can't use the fundamental theorem of calculus because the interval is infinite. The fundamental theorem of calculus says that if you have a function which is continuous on a closed interval from a to b, where a and b are both finite numbers. This, however, is not like that. A is finite, but in this case we're going off to infinity. So the fundamental theorem of calculus does not apply here. So what should we do? Well, we're going to take inspiration from our previous example. We're going to pick some number here, which we might as well call t, and we're going to look at the definite integral from a to t. So in this particular case, because I've drawn a function which is above the x-axis, the definite integral is going to give us the area underneath the curve. This is something which is finite. You can see that it's in a bounded region, so it is finite. And it's something that we can compute using the fundamental theorem of calculus. So what we're going to do is we're going to compute the definite integral from a to t of f of x dx, and then we're going to allow t to go off to infinity. That's the idea. So it's the limit as t goes to infinity of the integral from a to t f of x dx. And that's how we're going to define this. So the remark that we want to make is that we cannot evaluate the integral from a to infinity of f of x dx using the fundamental theorem. Because the interval is infinite, or is not finite in length. Remember, the fundamental theorem of calculus tells us that if f is continuous on an interval from a to b, so this is the fundamental theorem. So if f is continuous on this interval, where b is a finite number, then f has an antiderivative, and the integral from a to b of f of x dx is equal to that antiderivative at b minus that antiderivative at a. But that doesn't apply here because b is infinite in this case. So the fundamental theorem doesn't apply. However, we can apply the fundamental theorem to evaluate the integral from a to t f of x dx, because f is continuous on the interval from a to t, and here t is a finite number. I just noticed that in our original statement I didn't include a. Let's include a here. All right, so f is continuous on the interval from a, including a, but going off to infinity. So we can't evaluate the interval from a to infinity using the fundamental theorem of calculus, but we can apply the fundamental theorem of calculus to evaluate the integral from a to t. And then you can compute the limit as t goes off to infinity. T goes off to infinity, and that can be our definition for this improper integral. So yeah, let's leave it circled and let me label this as the definition. Let's actually see how this works. Let's look at an example. So example, let's compute the integral from, let's say, 3 to infinity of 1 over x squared dx. So here our function f of x is 1 over x squared. That's not continuous at 0, but our interval is from 3 to infinity, and that is continuous. So it's continuous on the interval from 3 to infinity. It's only around 0 that we have a problem with continuity. So this looks like, if we were to graph this looks something like this. And we can imagine that 3 is over here somewhere. And we want to compute the integral, the definite integral, or really the improper integral, from 3 to infinity. All right, well, we actually computed the improper integral from 0 to some number, and we found that that was infinite. But in this case, going from 3 to infinity, it will turn out that this is a finite value. So how is this going to work? Well, again, we're going to pick some number t here, and we're going to compute the integral from 3 to t, and then we're going to let t go off to infinity. So the integral from 3 to infinity of 1 over x squared dx is going to be equal to the limit as t goes to infinity of the integral from 3 to t, 1 over x squared dx. You don't need to write t goes to infinity with a minus there. You don't need to indicate that t is approaching infinity from the left side, because you can only approach infinity from the left side. So you don't need to put any little minus sign there. Okay, so this is a definite integral that has an answer in terms of t. So this is the limit as t goes to infinity of the integral from 3 to t. Let me write this as x to the negative 2 dx. So this is x to a power, so we can use the power rule. So this is the limit as t goes to infinity. You increase the exponent by 1, and now divide by that new exponent from 3 to t. All right, so this is the limit as t goes to infinity of minus 1 over x from 3 to t. So that's the limit as t goes to infinity of minus 1 over t minus a minus 1 over 3. And this is the area between 3 and t. So the area here is equal to 1/3 minus 1 over t, if I can just swap the order of those. So that's the area of this region right here. Now, as t goes off to infinity, it's going to get much bigger. Well, maybe not much bigger. Notice that it's 1/3 minus something, right? It's 1/3 minus something. So that means that this area is necessarily smaller than 1/3. However, as t goes off to infinity, this term, 1 over t, that goes to 0. So this is going to be equal to 0 plus 1/3 equals 1/3. So the area of the whole region, the total area, is 1/3. If you go from 3 to t, it's going to be 1/3 minus 1 over t. And it depends on t, because if I move t along, that means I'm going to be subtracting something smaller until towards infinity, the thing that you're subtracting is so small that it doesn't contribute anymore. So the limit is 1/3. And so that means that this infinitely long region going from 3 to infinity is actually has a finite area, an area of 1/3. Let's do another example. Let's look at the integral, let's say from 2 to infinity of 1 over x dx. We looked at a problem like this going from 0 to something, and we found that it diverged. That's going to happen here too. In this case, we have the integral from 2 to infinity of 1 over x dx. This is equal to, the picture looks very much the same as this one. We can even draw it, but it will look essentially the same. So it will look something like that. And let's say 2 is over here. And again, the region that we're interested in is infinite in length, going from 2 to infinity. So this is the limit. So once again, we're going to pick a t, then we're going to compute the definite integral from 2 to t, and send t off to infinity. So it's the limit as t goes to infinity of the integral from 2 to t, 1 over x dx, which is the limit as t goes to infinity of ln of x from 2 to t. Now, I'm not putting in the absolute value here because everything's positive. X goes from 2 to t, so I don't need the absolute value because the absolute value of x is just the same as x. So this is the limit as t goes to infinity of ln of t minus ln of 2. Oops, that's supposed to be like that. But ln of t, as t goes to infinity, this thing goes to infinity, so the answer is infinite. So the first one that we looked at, this one converges. And the second one, this one diverges. This integral diverges. So once again, we mentioned this in the last video, but let's write it down as a remark. If the limit defining an improper integral exists, we say the integral converges. If the limit does not exist, and that includes being equal to infinity, we say the integral diverges. So in our first example, the integral is finite, so the limit is finite, so the integral converges, and in the second, the limit is infinite, so that means the limit doesn't exist, so the integral diverges. We can have a theorem here, which corresponds to one that we saw before, and the theorem is that for any a greater than 0, the improper integral from a to infinity of 1 over x to the p dx equals, well, we saw an example here where we started with p equals 2, and that converged. So if you have a p which is greater than 1, it will converge. So this will converge if p is greater than 1. And that's what we saw here. P was equal to 2, which is greater than 1, and that gave us something which converged. So if p is greater than 1, you get convergence. However, if p is less than 1, then it's going to diverge. So it diverges if p is less than 1, or in fact equal, because this is the case, this case right here, this is the case where p is equal to 1. So it diverges, so it converges if p is greater than 1 and diverges if p is less than or equal to 1. Okay, so that's case 1. So case 1 is when you're looking at an interval which is infinite. You're going from a off to positive infinity. Case 2 is very similar. Case 2, if f is continuous on an interval from minus infinity to b, where we're including b, it's still an infinitely long interval, but it's just going from minus infinity to b. So f is continuous, then we're going to define the integral in pretty much the same way. The integral from minus infinity to b of f of x dx is equal to, and so now what kind of picture are we looking at? It's basically the mirror image of the kind of thing we were looking at before. So we're going to have b, well, b can be a positive number, but the idea here is that we're going off all the way over to negative infinity. So what are we going to do? You're going to pick some number which you're going to call s, and then you're going to compute the definite integral between s and b, and that's going to be something you can use the fundamental theorem of calculus to compute, and then you're going to send s off to negative infinity. So this is going to be the limit as s goes to negative infinity, the integral from s to b f of x dx. And once again, if that limit exists and is a finite number, then you say the integral converges, and if the limit does not exist or is infinite, which means it doesn't exist, then you say the integral diverges. So let's do an example of this kind of thing. So example, let's look at the integral from minus infinity to, let's just say 0, of e to the x dx. All right, now if you graph this, it's going to look something like that. So let's say that this is 0 here, and we're going to go off to negative infinity this way. So we're going to pick an s, which is here, and we're going to compute the definite integral from s to 0. And then we're going to compute the limit as s goes to negative infinity. That's our objective here. That's our plan. S goes to negative infinity. So the integral from minus infinity to 0, e to x dx, is the limit as s goes to negative infinity of the integral from s to 0, e to the x dx. This is a definite integral which we can evaluate using the fundamental theorem of calculus. So we have the limit as s goes to negative infinity. The antiderivative, or an antiderivative e to the x, is e to the x. This is from s to 0. So that's the limit as s goes to negative infinity, e to the 0 minus e to the s. E to the 0, of course, that's just equal to 1. But what about this term? Well, s is going to negative infinity. So we're looking at this curve here, or let me do it with the pointer. We're looking at this curve. This is y equals e to the x. So we're looking at this curve, and as s goes to infinity, or to negative infinity, the curve goes to 0. So this thing goes to 0. So that means we have 1 minus 0, which is 1. So that means the area, since this is a positive function, the area underneath the curve from negative infinity to 0 is 1. Now if you integrated it on the other side, you'd get a far different answer. So the integral from 0 to infinity of e to the x dx, this is the limit as t goes to infinity. The integral from 0 to t e to the x dx is equal to the limit as t goes to infinity of e to the x from 0 to t, which is the limit as t goes to infinity of e to the t minus e to the 0. And of course, e to the 0, that's still 1. But here we're looking at e to the t as t goes to positive infinity. So as you go to positive infinity, this thing explodes. It becomes huge. It becomes infinitely large. So this thing goes to infinity. So your limit is infinite, or it doesn't exist. So you can have very different behavior depending on whether or not your limit is from minus infinity to something or from 0 to positive infinity. It just depends on your function. So now we've seen the two cases. Well, there is of course a case 3, which is when you have a mix. So case 3. So if f is continuous for everything, so on the interval from minus infinity to infinity, then if you want to integrate from minus infinity to infinity f of x dx, you break it apart into two separate integrals. So it's minus infinity to any number will do. You just put a c there. F of x dx plus the integral from c to infinity, f of x dx. C is equal to any number, any finite number. C equals 0 is a common choice. And the basic idea is if both the integral from minus infinity to c, f of x dx, and the integral from c to infinity of f of x dx, if both of those converge, then your original doubly infinite, so the integral from negative infinity to infinity of f of x dx, converges. If either diverges, then the doubly infinite integral from minus infinity to infinity of f of x dx diverges. So, for example, if you look at the integral from minus infinity to infinity of e to the x dx, this is equal to the integral from minus infinity to 0, e to the x dx, plus the integral from 0 to infinity, e to the x dx. Now, we've already shown that this first one is equal to 1. We did that right here. So this is equal to 1, but this thing diverged. So if either one of these pieces diverges, then the whole thing diverges. So the integral from minus infinity to infinity, e to the x dx, diverges. So those are the three cases for improper integrals having infinite intervals. There is one other topic that we want to talk about related to improper integrals, and that's the comparison test. Comparison test for improper integrals. And basically the idea is that you're comparing two improper integrals because maybe you know one and you want to use that to determine if the other one converges or diverges. So let's start this way. suppose f and g are continuous functions on some interval. Now, it might be that this is an infinitely long interval, or it might be that it's a finite interval and f and g are continuous on it, but discontinuous at an endpoint. So suppose f and g are continuous functions on some interval that we're going to call I. And suppose you want to determine if one of them converges or diverges, and you want to use the other one to do that. Well, here's the idea. Let me just erase that bit of the line, and we'll put a period here. Okay. So there are two statements that we can make. So if the integral, well, let's call this interval, let's say, from a to b. Let's call it that. So suppose f and g are continuous functions on some interval from a to b. We don't know if they're continuous at the endpoints. These are improper integrals. So they might be continuous at one endpoint, or they might be discontinuous at both endpoints. We don't know. But if the improper integral from a to b of f of x dx converges, and if f of x not f of x dx, but if f of x is greater than or equal to gx, which is greater than or equal to 0, then what does that tell us? Well, we're assuming that f is bigger than g. We're assuming that everything's positive, so we can think about this in terms of area. So what do we know here? What do we know? We're thinking about this in terms of area. Let me just move that down a little bit, like this. So we know that f is bigger than g. And we're looking at the integral from a to b. Now, there might be an infinite discontinuity. Let's actually just assume that there is an infinite discontinuity at a. Now, what we know is that these are both positive, and we know that f is bigger than g. So we have an infinite discontinuity at a. So let's say that this is y equals g of x. Now, what we know about f is that it's bigger, so it's going to look something like that. What else do we know? Well, we know that the integral from a to b converges for f. So that means that the area underneath f is finite. But g is smaller. So that means the area under g is even more finite, so to speak. It's even smaller. So if I shade in this region underneath g, so this is the improper integral. This is the improper integral from a to b. And we can see that the area from a to b is smaller than the area underneath f. So if you know that the integral from a to b of f converges, that means it has a finite area. And if it has a finite area, then that means the smaller area, which is shaded blue here, that's finite too. So our conclusion is that if the integral from a to b of f of x dx converges, then so does the integral from a to b of g of x dx. Then this converges as well. So that's the first statement. So if you know that f is bigger than g, and you know that the improper integral of f converges, then the smaller improper integral of g, that must converge as well. Well, what's the second statement? If there's one, there's probably a two. And it says that if the integral from a to b of f of x dx diverges. And if, in this case, you know that g is bigger than f of x, which is 0, which is greater than or equal to 0, then what does that tell us? Well, now we're looking at a different picture. The functions are still assumed to be positive, so that means we're thinking about things in terms of area. So let's suppose that this is a here, and we're going to have some b here. And again, we'll assume that there's some infinite discontinuity at a. So g is bigger. So let's say that this is y equals g of x. And we know that it's bigger than f, so f is underneath somewhere, something like this. So y equals f of x. And now what we're assuming is that the area underneath f is infinite. That's what we're assuming. Because we're assuming that this integral diverges, so that means it's infinite area. The only way, if your function is positive, so if it's positive, the only way you can have a diverging integral like this is if the area is infinite. So what do we know about g? So then the integral from a to b of g of x dx. Well, if g is bigger than f, and we know that this area is infinite, and we know that g is higher up, so that means there's more area underneath it than there is for f. That means, well, it must be finite, must be infinite too, so this also diverges as well. So we're assuming that g is bigger than f, and we're assuming that the area underneath f is infinite. So if g is bigger than an infinite area, then, well, or I should say, if the area under g is bigger than the area under f, and that area under f is infinite, then the bigger area has to be infinite as well. So that is the second statement for the comparison theorem for improper integrals. So we have here two cases, but be careful, because if you don't have this setup that you see here, either the first one or the second one, then the comparison theorem doesn't tell you anything. So note, if you know that the integral from a to b of f of x dx is finite, so converges, and if you know that g is bigger than f, what does this tell you? Well, let's look at our picture again. So again, we're looking at something that looks like this. This is going to be our a, this is going to be b over here, and again, we're assuming an infinite discontinuity at a, but it doesn't have to be at a, it could be b. This is just to illustrate it. So g is bigger. So this is y equals g of x. That's bigger. And then we have y equals f of x. That one's smaller. So what do we know? We know that the area underneath the curve from a to b is finite. We know that because it tells us that the integral, the improper integral from a to b of f of x dx converges. So that means the area is finite. So that means it's some number. It could be 12 for all we know. Well, what does that tell us? Well, what does that tell us? So what does that tell us about the convergence of the improper integral from a to b of g of x dx? Well, the answer is nothing. It doesn't tell us anything. We know that this area under f is finite. We know that, for example, it's 12. We also know that G is bigger, so the area underneath G is bigger. Well, 13 is bigger than 12, so maybe the area is finite and just some larger number, but it might be infinite. It could very well be that there's an infinite area underneath G. Infinity is bigger than 12, so it would be a consistent statement to say that G is bigger than F, but G is infinite and the integral diverges. But it's also a consistent statement to say that the area under G is finite, but just some larger number than the area under F. So if the area under F is 12, maybe the area under G is some finite number bigger than 12. Maybe it's 1,000. We don't know. We just don't have any information. So you have to be careful when you're looking at the comparison theorem for integrals that you have the information in the right order. Otherwise, you can't draw a conclusion. I did these examples for an infinite discontinuity, but the same is true. So let me write this down. So we illustrated, or we looked at examples with an infinite discontinuity. That's supposed to be a C. Discontinuity at the left endpoint. However, the same is true if, for example, the discontinuity is elsewhere in the interval. So let's say at the right endpoint. Or anywhere else, because you have to, if you have an improper integral with the discontinuity in the middle, you have to break it apart into two separate intervals. Two separate integrals over different intervals. One where you'll have the discontinuity on the left and one where you'll have it on the right. But it's also true if you're looking at not a discontinuity but an infinite interval. So the same is true if you are integrating over an infinite interval. So you could just replace the integral from a to b of f of x dx. So replace this integral with the integral from a to infinity f of x dx, or the integral from minus infinity to b f of x dx, or indeed from minus infinity to positive infinity, because if you have something like that, you have to break it apart into two separate integrals, one dealing with minus infinity and one dealing with positive infinity. So even though I only illustrated it with one specific type of improper integral, it's still the same thing is true for the other types. And that is the comparison theorem for improper integrals. What do you use it for? What is it good for? The basic idea, let me just fix that. What is it good for? The basic idea is maybe you want to show an integral converges or diverges, but you can't compute it directly. So let's look at an example. Suppose that we wanted to show that the integral of 1 over 1 plus x to the 4 dx from 3 to infinity we want to show that this one converges or diverges. Now, we might have some difficulty computing this one directly. So instead what we do is we compare it. Well, what do we compare it to? We can compare it to something that maybe it looks like. So for example, 1 plus x to the fourth is bigger than x to the fourth. That's certainly true. So 1 over 1 plus x to the fourth is less than 1 over x to the fourth. In this picture here, this is your function g. And this, 1 over x to the 4, this is your function f of x. Now what I know, or what we know that the integral from 3 to infinity of 1 over x to the 4 dx converges. You could compute this exactly, but we don't have to because we have a theorem just up here a little ways. If we find it, we can go up here. Theorem. For any a greater than 0, the improper integral from a to infinity of 1 over x to the p dx converges if p is greater than 1. Well, here we're looking at p equals 4. P is equal to 4, which is greater than 1. So we know that this one converges. And furthermore, we know that 1 over 1 plus x to the 4 is smaller than that. So the integral from 3 to infinity of 1 over 1 plus x to the 4 dx is smaller than the integral from 3 to infinity 1 over x to the 4 dx. And we know that this one's finite. So that means the integral from 3 to infinity of 1 over 1 plus x to the 4 dx is finite too. So it converges. So the integral from 3 to infinity 1 over 1 plus x to the 4 dx converges. And that's how you use the comparison test for integrals. Let me just fix this. 1 over 1 plus x to the 4 dx. Because the idea is maybe we want to show that this one converges, but we can't compute it directly. But we know that it's smaller than something that converges, so it must converge too. So that's how the comparison theorem works.